Hello, I'm Niels Martin Larsen. I'd like to present the paper Digital Workflows for Natural Wooden Constructions. The paper is written with my colleagues Kruse Aagaard and Lynn Kieffer from Aarhus School of Architecture in Denmark. Human behavior changed the ecosystems of the earth. To build, we excavate, mine, harvest and transform large areas of land. The consequence is the creation of biological uniformity, dying species, and the vast regions of monoculture. The timber industry is an optimized machine that delivers wood to a market defined by standardization, that is, straight equal-sized materials, and this is obtained through plantation with straight-grown trees. However, plantation forestry impacts biodiversity, and the current practice of timber production is often degrading the forests. So to be able to position wood as a truly sustainable resource for buildings, the industry would have to change. The building design needs to adapt to the natural properties of wood and thereby accommodate a more sustainable timber production. So we try to reconsider how timber is used in construction. We look at the possibility of using crooked trees and thereby achieve better use of resources and forestry with larger biodiversity. Modern sawmills use CT scanning to create exterior and interior point clouds of the logs. The logs are sorted into categories, and one category is logs that are too curved for being used in production. So a pile of discarded wood with matching point clouds is discarded. We teamed up with the Technical University and the Niels Bohr Institute and did a series of CT and X-ray scans to study the interior of wood and how these technologies work. We also performed a series of 3D scans on saw logs, and we started to experiment with machining strategies that follow their shapes instead of breaking them. Our concept is to match the curved saw logs with geometries and utilize the natural shapes of the logs in various construction types. Oak trees are curved, twisted and crooked, and they are extremely strong. Often only 40% of an oak is used at the sawmill, the rest becomes firewood. The Vikings used oak for shipbuilding. They used natural curvatures to define the shape of the boat, and mirrored cleaving of the logs for the sides, in order to keep the wood fibers intact and gain the maximum strength. Crooked logs have also played an important role in traditional Nordic and Danish architecture. The crooked logs were intentionally used in farmhouse construction for either aesthetic or practical reasons. We are inspired by a growing research field that makes use of scanning technology and robotic fabrication for wood processing and construction. But we try to develop a method that is less specific in terms of the stock material and allows a high degree of control over the manufacturing and placement of the construction parts. The method consists of a series of steps that are closely connected. The first part is to establish a database of saw logs. Each saw log is scanned and analyzed into a NURBS representation, which is saved with information about location, quality, species, and dimensions. An overall design solution is defined, here in the form of a lamellar roof structure. A custom script distributes the material in the structure, and TOOLPATH for the robotic fabrication of each member is automatically generated. We use computational simulation and physical testing to develop the workflow. So we pick up oak logs at a local sawmill. Before the scanning, the saw logs are marked with 3 red dowels for later positioning. We scan the logs with a focus laser scanner. The point cloud from the scanning of the saw log is processed with the Volvox plugin and custom scripts for Grasshopper in Rhino. The main task is to define a center curve, since this is used for the selection and placement of logs. The end planes found from the scanning sets the overall direction. Along this straight line between the planes, a series of sections from the point cloud is then extracted. The centroid of each ring gives us points that lie inside the sections. From each of these points, a set of radial lines is then created. For every line, the closest points in the corresponding point rings are found, thereby creating a new set of point rings. These new points are well ordered as the hours on a dial, and therefore allows the construction of rationalized NURBS curves describing sections through the log. The area centroid of each section is then used for defining the center curve. To get an even distribution of isocurves, a new set of radial lines and corresponding sections are constructed from the center curve, and these are used for defining the NURBS surface representation of the log. This lightweight geometric information is saved in the database together with information about the quality, storage place, and overall dimensions. At this stage in the workflow, we now have a database of available logs. Each log is placed in the construction where the curvature matches best. Currently we are working with a Solinger principle. This is partly because it can be used for curved surfaces, but also because the structure consists of only short members, which is what we can produce in our robot facility. So the system will go through each member of the structure and compare the curve segment with the center curves of the logs in the database and find the best match. Here we see how the system compares each log with a curve segment. The log is rotated to match the segment's curvature and different positions are analyzed. The log with the smallest deviation is selected. Finally, all the segments in the structure has a log assigned to it with a specific position. This process takes a few seconds, depending on the design and the size of the database, of course. The next step is to generate the positioning of standard joints for each node. The toolpaths for milling are generated just before each component is fabricated. By offsetting the initial cutting surface, the layering of toolpaths can be defined. The physical logs are positioned on a rotary table. For positioning the log in the robot cell, we use the red dowels and OptiTrack motion capture. We've been testing different types of robotic machining, but in this setup, the robot is equipped with a spindle for milling. Here are some prototypes that are milled. On the right side is a prototype where we have processed 3 sides of the log, trying to find a good balance between a nice finish and the original shape of the wood. Here is a prototype where we've tested the design of the joints and the transition between the components. We are now working on producing a larger prototype based on the stockpile we have available at the moment. In the autumn, we'll be working with traditional craftsmen at the Open Air Museum at Hjalhed in Denmark to realize a small test building based on the method. Thank you very much for listening.